Okay, so this is the first lecture for second semester pre-calculus, and I want you to read section 4.1 and 4.2. We're going to kind of cover both of those. We may end up having two videos, but we'll see how long this takes. But I think most everyone's had geometry, and in geometry we dealt with angles between typically 0 and 180 degrees. And we'll get back to triangles at some point, but right now we're going to kind of do two things. We're going to expand the idea of angles, for one thing, not to just triangles, and also to angles greater than 180 degrees. So let's kind of review what I just talked about. We've looked at triangles before, and so I'm going to draw two triangles. So where all the angles are less than 90 degrees. Actually, three types of triangles. So, we would call this an acute triangle because all of the angles are less than 90 degrees. Okay. Then you have a right triangle. That's where one of the angles is 90. So make this 90. And as a consequence, the other two have to be less than 90. Remember, from geometry, the sum of the interior angles have to equal 180 degrees. So if this one's 90, then these two remaining angles have to be less than 90 because the sum has to be 90. And then you have an obtuse triangle. That's where one of the angles is greater than 90 degrees. And of course, if one is greater than 90, the other have to be less than 90. So this angle here is greater than 90 degrees. These are both less than 90 degrees. Now, another way of defining angles is not part of triangles, but it's looking at the Cartesian coordinate system. So I'm going to draw my x and y axis. And the standard way we define an angle is we put one of the sides of the angle along the x-axis. And then we take the second side of the angle and we point it some direction. It could point exactly here, then you'd have an angle of 0. If one's pointing in the y direction, one's pointing in the positive x direction, that's 90 degrees. If they point opposite each other, that's 180 degrees. If one is pointing in the positive x and one is pointing in the negative y, that's 270 degrees, and then you come all the way around, and that would be 360 degrees. So let's just start off in the first quadrant. So what are the quadrants? So you can see as I rotated this line around, I pointed into the different quadrants. Okay, the first quadrant is where both the x and y are positive. So x is positive, y is positive. That's the first quadrant. Now the angle is this relative position between the two sides of the angle. And a lot of times we use the Greek symbol theta to do this. There's other Greek symbols that we use for angles, alpha, beta, gamma. But theta is the one we kind of use as a default. And one way to define this angle is if we were to create a right triangle out of these two sides. So I'm going to draw a vertical line here such that this angle, this triangle that I've created where one side is the same direction as this side of the angle. So this, this angle doesn't have to keep going. It can keep going. So it starts at the origin, it's a ray, and it goes off to infinity. But I could pick a vertical line somewhere and create this right triangle. So we have a 90-degree angle between the positive x-axis and this vertical side of the triangle. So in this case, we can create a right triangle, and we can, define if this ray is pointing up vertically, then we have, yeah, well, actually, when you do that, you're not going to even have a triangle. So kind of in the limit, when this angle gets, well, when this angle becomes larger, and this one's 90 degrees, this angle has to get smaller, smaller, smaller. Okay, so that's kind of the way you might be able to think it from historically in geometry perspective. Now, another way of defining a circle is, I mean not a circle, but an angle, is to draw a circle with the origin being the center of the circle. And instead of thinking of this as a right triangle situation, what we do is we think of it as a part of this circle. So I'm going to take this and move it out of the way. Get rid of this little right angle thing. So if we have a circle, we have a radius of the circle. And no matter where we go around on this, if we pick a point on this circle, all these points on the circle are going to have a certain radius r. And then there's also this distance s, which is the length along the arc. Now if we go all the way around the circle, that'll be the circumference of the circle. So these arcs represent a proportion of the entire circle. And so instead of using degrees, what we do is we use what are called radians. So let's introduce radians. We'll come back to this quadrant thing in a second. But so the angle theta in radians is defined not by, a full circle is 360 degrees, and then the angles between 0 and 360 degrees are proportions of that. What we do is we say the angle in radians is the ratio of the distance along the circle to the radius of the circle. And if you take another circle and you just increase the radius, if you increase the radius by 50%, then the arc length S will also increase by 50%. And so for a given ray that goes out in this direction, no matter what radius circle you use, the ratio of the arc length to the radius is the same along this path. Now both of these are distances. So this is a distance. You could do inches, and this distance is inches. So the units for radians are inches, or inches per inch. They could be meters per meter. It doesn't really matter what your system units are for measuring it. You can see the units cancel out. And so what we call this ratio of these distances is radians. So one thing we could say is, 360 degrees, we know that is when you go all the way around. Start at some reference location, which is the positive x-axis, and you rotate this second ray all the way around. That's 360 degrees. Now, from the equivalent situation in terms of this angle measurement using radians is that the distance that you travel along the arc is going to be, so let's write this distance along the arc divided by the radius. So that's just the definition of radians. Well, the distance along the arc is the circumference, and the denominator is the radius. And we know from previous experience that the circumference of a circle is 2 pi times the radius. So if you take 2 pi times the radius divided by the radius, you get 2 pi. So what we can say is 360 degrees an angle of 360 degrees is, so let's erase that. So an angle of 360 degrees is equivalent to 2 pi radians. Now remember, pi is this number 3.14159. It's an irrational number, so it cannot be represented as a fraction, and it has an infinite number of digits. And it's the ratio of the diameter to the circumference. Okay, so if 360 degrees is equivalent to 2 pi radians, we could say 180 degrees is equivalent to pi radians. 90 degrees is equivalent to pi over 2 radians. So all we're doing is we're saying half of 360 is 180, half of 2 pi is pi, half of 180 is 90, half of pi is pi over 2. So we did it again, 45 degrees. That's equivalent to pi over 4 radians. So we have this conversion. So to convert degrees to radians, what we do is you multiply, or actually divide, well, you multiply by 180 and divide by, did this wrong, you multiply by 2 pi and you divide by 180. Okay, so let's just do an example. So let's say theta is given as 52 degrees. So to convert theta in degrees, you take 52 degrees, you multiply by 2 pi radians. So there are 2 pi, well, yeah, and I just did this wrong. This should be pi. Sorry, pi. I'll do it based on the circle. So we know there are 2 pi radians per 360 degrees. If you simplify this down, you'll get pi divided by 180. So that's where that comes from. But you can remember 2 pi is the same as 360 if you're trying to remember. So we'll go ahead and use the simplified version here. So you have 52 degrees times 2 pi divided by 360. And if you want to convert pi to a decimal, or just use that pi on your calculator, so if I take 52 times 2 times pi, which is 3.14159, divided by 360, I'll get 0.907 radians. Or I could take 52 degrees times pi divided by 180. All I'm doing is dividing both the numerator and the denominator by 2, and you'll get exactly the same answer. So radians are always a lot smaller than degrees. Pi is about 3, so you're going to have 3 over 180. Now, to convert the other direction, convert radians to degrees, you're going to multiply by 180 and divide by pi. So let's say let's say theta is given in radians, so it's 2.7 radians. So all I have to do is take 2.7 radians and multiply by 180 divided by, so that's 180 degrees per pi radians. 2.7 times 180 divided by pi. So I get theta is equal to 154.7 degrees. So likewise, if you have a radian number, the degree number is much higher. You know, if you have 2 pi radians, that's going to end up being, should convert to 360 degrees, and the other way, 360 degrees should convert to 2 pi radians. So that's the conversion between the two. That's the definition of theta. So why is this important? Well, because in a lot of mathematics, physics, engineering, the calculations are much simpler if you represent theta in terms of radians than if you do it in degrees. Also, the units here are kind of zero. I mean, not zero, but there are no units. You know, it's length per length. Here we have this arbitrary decision to call a full circle 360 degrees based on, you know, it's about 360 days in a year. So it's the whole idea of using degrees is a little bit less fundamentally based. Okay, so let's go back to this quadrant. So if I were to have this second ray pointing somewhere in this direction, well, in this quadrant, in this part of the graph, we call this quadrant 2. Here x is negative and y is positive. So here negative x, positive y. Then if we have the second ray pointing down this direction, so this is what we call quadrant 3, and you know, here we have negative x and positive negative y. So they're both negative. You can just think of this as coordinates, negative, negative. So we call that quadrant 3, and then finally, if we have the second array compared to this reference direction, that we call this quadrant 4, Q4, quadrant 4. Here x is positive, y is negative. It's positive y, x, negative y. So we call that the fourth quadrant. So you start here where both x and y are positive, and then you rotate around counterclockwise this way. So the first thing you come to is the second quadrant. That's why it's Q2. Then you come into the third quadrant, the next situation where both x and y are negative. Then you come into the fourth quadrant where x is positive, y is negative, and then you start all over again. Now, one other thing about this kind of situation versus triangles is triangles you had angles between 0 and 180 degrees. Here we can have positive angles, which can go to 360 or 2 pi radians. But you can keep going too. You could start going around and around again. So each the angle, say this angle by this, using this initial example here, you know, it maybe is around 1 radian. If I go all the way around, it's going to be 1 radian plus 2 pi, but it's the same position of this second ray relative to the reference direction, which is the positive x-axis. So I can have this relative position of these two rays can take on multiple values in terms of the angle, and they all are multiples, or they're some value plus 2 pi, plus 4 pi, plus 6 pi, plus 8 pi. And you can also go negative. So instead of going from this point and going counterclockwise, we could go clockwise and go all the way around here. So you can have both positive and negative angles. You can do it in degrees and you can do it in radians. So that's one of the big differences between geometry and trigonometry. Trigonometry allows you to have angles basically from negative infinity to positive infinity, whereas for right triangles we typically are between 0 and 180 degrees. We don't do radians in right triangle geometry. Okay, so we talked about that, about conversion. Let's just formalize what this thing is where you have the same angle, but so what I'm going to do is, here's an angle. I'm going to superimpose on that a y-axis and an x-axis. So the x-axis is going to line up with this side. And we call this angle theta. And let's just say, for argument, it's 1 radian. Now if I take this ray, and instead of just coming from here to here, let me go all the way around and then do the same part. So this angle could also be represented as 1 plus 2 pi radians. Now for me, whether I do it 1 radian or I do it 1 radian plus 2 pi, it looks exactly the same to me. Unless you go through the actual process of looping it around, you don't know it. So what we could say is that 1 radian and 1 plus 2 pi radians are co-terminal angles. Coterminal means that they look exactly the same, even though one has just gone from here to here and one has gone all the way around one time to there. So we could, I could list a bunch of angles that are coterminal with 1 radian. 1 plus 4 pi, 1 plus 6 pi, 1 plus 8 pi. So all of these are coterminal angles. I could also do one. What I could do is I could go up 1 unit and then go around negative 2 pi. So you can also subtract 2 pi, 1 minus 4 pi. So all these angles, we would say they are coterminal angles, because they have the same relative position between the positive x-axis and where the second ray goes. And they're going to have the same trigonometric properties. Okay, so that's 4.1.